In this video, we want to continue with some non-obvious u substitutions. So anyway, here's one, tangent of x. In fact, this one is so non-obvious because there's not an inside, there's just one function. However, I know the derivative of the tangent x is the secant squared x, but I don't know that we know how to integrate the tangent x. And the way we do it, actually, is to write it as a fraction, sine x over cosine x. I remember learning trig, and my fallback was always, I like sines and cosines, and all the other trig functions can be written in terms of sines and cosines. So this to me was just sort of a natural thing. Hey, I don't know what to do with tangent. Let me write it this way and see what it looks like. Well, now this looks like something where, hey, I see sine and cosine, which are derivatives of each other, and, well, up to a minus sign anyway. But if I let u equal the denominator here, cosine x, then du is minus sine x dx. The derivative of cosine x is minus sine x. And so, except for minus sign, I've got the du there. So if I throw a minus sign in and take a minus sign out, essentially multiply by -1 and then multiply by -1 again, I've got minus the integral of 1 over u du. The 1 over u is the 1 over cosine x, right? That cosine x in the denominator. And then the minus sine x dx is the du, right there. Minus sine x dx is du. Now that's just minus the natural log of the absolute value of u plus a constant, which is minus the absolute value, the natural log of the absolute value of the cosine of x. Oops. Now, it's generally not written this way because what they do is they take this -1 that's being multiplied out in front and put it as an exponent. So this would be the natural log of the absolute value of the cosine of x to the -1 power. But the cosine of x to the -1 power, right, means do 1 over the absolute value of the cosine of x. Well, 1 over the absolute value of the cosine of x is the absolute value of the secant. So it's usually written this way. The integral of the tangent, I'm going to just write this down, the integral of the tangent of x is the natural log of the absolute value of the secant of x plus c. Eventually you do this enough times and that's one of the ones you just remember how to do, that you don't need to go through the steps every time. But until you get to that point, and I can't tell you how many times I've done this integral just because as I was a student and learning it, I couldn't remember things. I don't like remembering things, I like being able to figure it out. And I could see this process of turning it into sine and cosine and then doing a u substitution, which gets me to that. Okay. So there's one example of a non-trivial u substitution, non-obvious anyway. How about this one? The integral, here's a new example, the integral of x squared times the square root of 2 plus x. Okay. Now this one definitely doesn't look right because inside the parentheses, inside the inside function here, 2 plus x, the derivative is just 1 dx, and you've got this x squared out there. It's like, what? Maybe the u would be x squared, but then the derivative would be inside, and no, this is just weird. However, what we can do here is let u equal the inside. Let u equal 2 plus x. Remember, I can do anything I want, and so can you. But once you make that choice, you're obligated to do it right. Okay, so if I let u equal 2 plus x, what's du? Well, the derivative of 2 is 0, the derivative of x is 1, so this is just dx. So now when I make the substitution back in, you might think, well, what do you do with that x squared? Well, here's something I haven't done yet with the u substitution. I actually can turn this around. Well, if u is equal to 2 plus x, then x is equal to u minus 2. So for that x squared, I'm going to turn it into a u minus 2 squared. And then I've got the square root of u here. And the dx is du? Yes. So the x squared was the u minus 2 squared. The square root of x plus 2 is just the square root of u. And then the dx just turns into a du on this one. Okay. And on this one now, where I the square root is tough to work with, this only being an x squared. I'm going to multiply that out as u squared minus 4u plus 4 times the square root of u. And then I can distribute that square root in. You got to be careful because square root doesn't distribute over stuff. But multiplying by the square root does distribute over this summation. So this becomes, and remember, this is a u to the 1/2 power. So I've got an integral of u, this is a 2.5 power, so that's 5/2, minus 4 times u to, that's a 1.5, so 3/2, plus 4u to the 1/2 power du. Now I've got it written as a polynomial, or power function anyway, and this is a u to the, add 1 to this, that would be 7/2, and then divide by 7/2, so that's multiplying by 2 7s, minus 4 times, this is u to the 5/2, multiply by 2/5, because I'm dividing by 5/2, and then plus 4, I've got u to the 3/2, divide by 3/2, so multiply by 2/3. This is times plus c. So anyway, 2 7ths u, but u, remember, what was u? I don't remember. U is 2 plus x, so 2 plus x to the 7/2 minus 8/5 2 plus x to the 5/2 plus 8/3 2 plus x to the 3/2 plus c. Okay. What happened on this one? Let's review that. I did a u substitution which was not at all obvious. I just let u be a piece of this. It simplified that piece, but in simplifying that piece it complicated this one because the x squared had to now be a u minus 2 squared. However, it set me up in a place where I could do some algebra and work this into something that I can integrate, because this is definitely something I can integrate. It's just a u to a power, u to a power, u to another power. Okay. Sometimes this is the way you do things. You make u be something, particularly something inside that you want to simplify, and then take the consequences. If u is equal to 2 plus x, then x is equal to u minus 2. And you plug that in there for u minus 2. Okay. This integral I ended up with right here doesn't have any x's in it. I couldn't leave the x squared in there and say x squared square root of u. That doesn't make any sense. I got to get it all into u's. Okay. Anyway, there's a couple of interesting examples for you.